Welcome back to ACER Explained. In this video series, I'm going through section 3 of the ACER practice test booklet. So if you don't have that in front of you already, then bring that up so that you can follow along. In this video, I'm going to be going through questions 37 to 40. And as usual, I'm identifying prereq knowledge, reasoning skills, and bootcamp resources that could help. In Unit 11, we're given a diagram of a person that is jumping. And in that diagram, we have two distances. We have distance C, which is from standing to crouching in terms of the center of mass. And then we have distance J, which is from standing to jumping. So once you're off the ground. So you have your center of mass here. So this is standing, crouching, and then jumping. And then you have this, which is C, and this, which is J. All right. And then we're also given some formulae. So we have the first formula, which is the force that's required for a person to actually raise their center of mass by J. So basically the force that's required for you to leave the ground and jump. And we're told that it is K times their weight. And so weight is equal to mass times gravity. And so it's K times their weight. And this is something that we're given. And based on that, the sentence actually tells us that it's K times the weight. So you can derive the formula weight is equal to mg. So you didn't actually have to know this formula. It would have been useful so that you can kind of recall it quickly, but you're already kind of given that information. So you have these two here. All right, and m is mass, and then g is the acceleration due to gravity. All right, so thinking about, needing to jump, the force that's actually required to leave the ground has to be greater than your mass, right? Because your mass is the force that's pushing down when you're standing, and then the force that's required to jump, if you want to leave the ground, you have to have that force be greater than your weight. So F must be greater than W. And then based on this, you can kind of fill in KMG is greater than mg. And so you can divide both sides by mg, and you're left with, so dividing this by mg is 1, and k times 1 is 1, and dividing this by mg is also 1. So you're left with k is greater than 1. So this is the conclusion that you can come to for any sort of situation, including Earth and including the moon. Because if you think about it, if you have F is equal to km, let's say that the Earth's gravity is 10, and then your weight would also be on Earth, m times 10. And we're also given this information to assume that m is the same for all jumps, right? So that's fine. We can continue with this comparison, right? So then we have F must be greater than W because of what we discussed before here. So this is W, this is F. You have K, M10 must be greater than M10. So you can divide both sides by M10 and you get K is greater than 1. Okay, now let's say that we're looking at the gravity on the moon. Okay, so let's say F is equal to Km, and we're told that the gravity on the moon is 1/6 of that on the Earth. So let's say 10 over 6. Okay, and then your weight on the moon would also be the same thing. It would be m times 10 over 6. So then same thing, if F is greater than W, there we go, we're back. F is greater than W, then you have K, m 10 over 6 is greater than m 10 over 6, dividing both sides by m times 10 over 6. So you can divide this whole thing by itself, and you get 1, and you get 1. So you get K is greater than 1. So whether you're on the Earth or whether you're on the moon, K has to be greater than 1 in order for a person to leave the ground. So the answer is B. And this is all based on this knowledge here. So you have to have the basic understanding of motion and forces in order to conclude, make this conclusion about the fact that F must be greater than W. Once you can make that conclusion that F must be greater than W, that's when you can just fill things in and do basic calculations down here in order to figure out the values that are required for K. So like I said earlier, it's helpful to have a basic understanding of how forces and motion works. And the reasoning skills that you needed here were the calculations and formulae, but also just basic physics reasoning. So the resources that can help with this are the acceleration class on calculations and formulae, as well as the bridging course on work and forces for physics. So question 38 is asking us about if someone jumps 11 times as high on the moon as on Earth, and they're using equal force, how large is this force that's exerted by this person? So first of all, we're looking at our value J here because we're looking at how high somebody can jump. And looking at the diagram, value J is essentially the distance between the center of gravity when they're standing versus when they're in the air. So how high they can jump is determined by, well, it's measured by J. So we're looking at J. And because we're looking at J, we want to look at the equations that involve J, and that's these two equations that I've written here. But what I'm going to do first is I'm going to essentially translate this into an equation. So J on the moon, so how high somebody can jump on the moon, well, this person can jump on the moon, is 11 times how high this person can jump on the Earth when force is the same, using equal force, right? So now we have to look at plugging in or using these two equations to solve this equation that we've just derived from this sentence here. So what we want to do is we want to keep K constant in terms of whether or not it's on the Earth or the moon, and we're given Earth so that it's just simple. It's more simple to just use the K value for Earth so that we can actually solve for what we want to solve for, which is, in this case, we want to solve for K because C is constant here, and the only thing that's we're looking of in interest is K. And we also know that K is relevant to force because of our equation here. Force is equal to K mg. So we want to look for K. And so we want to keep it constant. We want to keep it K Earth, right? So we have J moon, which we're told is C times 6K Earth minus 1 is equal to 11 times this bit here, C times K Earth minus 1. And because we're using K Earth, I'm just going to simplify this just so that it looks a bit nicer. We're just going to use K because we're already using K Earth. We don't need to clarify whether it's moon or Earth. So I'm just going to do 6K minus 1 is equal to 11 times C K minus 1. And now C is there on both sides, so we can cancel that out, and we're left with 6K minus 1 is equal to 11 times K minus 1. And I'm going to expand this out. So 6K minus 1 is equal to 11K minus 11. So what I'll do here is I'm going to add 1 on both sides and just do our simple algebra. So 6K is equal to 11K minus 10, because adding 1 to negative 11 is going to get to 10. And then what I'll do is minus this on both sides as well. So minus 11K minus 11K. And what I get is negative 5K is equal to negative 10. So 5K is equal to 10. And I can divide that by 5. So K is equal to 2. Now what I can do is plug this into our original equation here. So force is equal to 2 times mg. Now we know that weight is equal to gravity times mass, right? Because force is equal to mass times acceleration. That's the basics of your physics that you will require to make this question a little bit more approachable. Is force is equal to mass times acceleration. So the force that is defined by weight is equal to the mass of the person multiplied by the gravity, which is the downward acceleration that we have, right? So we can say force is equal to 2 times W, because we know that W is equal to mg. So what this is telling us here is that the force that's being exerted by this person is 2 times their weight. And because we've been looking at K Earth this whole time, it's going to be 2 times their weight on Earth. And so C is our correct option here. So this question, it would have been helpful to have some knowledge on your kind of basic how forces and gravity works, just so that it's more approachable. But like I said in the previous question, you could have derived that weight is equal to mass times gravity from what you were given in the stimulus if you looked carefully. And so the reasoning skills used were calculations and formulae, as well as your physics reasoning. So the bootcamp resources that can help with this are the acceleration class on calculations and formulae, and the bridging course, work and forces. Alright, so question 39 is telling us if someone jumps on the moon using a force that's 6 times their weight on the moon, and if the same force is applied on Earth, what will happen? So let's look at our first equation, kmg. So it's very important to understand what these equations even mean, particularly what k means, because that means then you can plug things in from the text into the equation if you have that understanding, right? So it's saying there's a force that's 6 times their weight on the moon. Now, all this is saying is that the force is 6 times their mass times gravity on the moon, right? Because weight is equal to mg. And so 6 times their weight is 6 times mg, where g is on the moon, and we're told that m is a constant, so we don't need to worry about m. So this is the equation that we get here. And then we're asked what would happen if the same thing happened on Earth. So in order to kind of compare this to the Earth, what I'm going to do is F is equal to 6 times m times what we know about the gravity on the moon is that it's 1/6 that of the gravity on the Earth. So now if we think of it in terms of the gravity on Earth, we can compare it to what would happen on Earth, right? So basically it's saying, now I'm going to simplify this equation, is 6m times 1/6 g on Earth. All right? And so what we can do here is simplify it. So F is equal to 6 times 1/6 is 1 times the mass times gravity on Earth. Right? So this is what we get. We get force is equal to mg. So see how we took up here, we took this k value in order to figure out kind of the proportion of force, and then we applied it to the gravity that would exist on the Earth and tried to derive force from that. And what we got is F is equal to mg. And so in this scenario, k equals to 1, right? So over here, this is our k value, because F is equal to kmg, and if k is equal to 1, then F is equal to mg, right? So here k is equal to 1. And now we're going to go back to the first question, question 37, where we were told that in order to jump on the moon or on the Earth, k needs to be greater than 1. Because if the force that you're applying upwards is the same as the force that's being applied downwards by your weight, nothing is going to happen. These two are both going to cancel out. We need this upward force to be greater than the downward force, and that is represented by K being greater than 1. So what would then happen here is that because K is equal to 1 in this scenario, they will not leave the ground on Earth. And this makes sense because if you think about it, you have less gravity being applied on the moon, right? And if you think of, people jumping in space, it's like quite easy to apply a small amount of force and float up into the air, right? And so if you were to apply the same kind of force on Earth, it would result in you potentially just walking normally and remaining on the ground. And so logically this makes sense. So you can also kind of check your reasoning in that sort of a sense. And so you can circle A and move on to the next question. So again, for this question, if you had that basic knowledge on forces and motion, then, that's all good. That will help you kind of come to these conclusions a little bit quicker and feel more comfortable with this kind of a question, but it wasn't necessary. And the reasoning skills that we used here were calculations and formula, and very importantly, being able to kind of convert text into formula, and knowing when to use which formula is very important, and knowing what your text is telling you in terms of how to then apply that to your formula. That skill is also quite important. And so the bootcamp resources that can help with this are the acceleration classes on calculation and formula, as well as in terms of that previous knowledge, the bridging course on work and forces. So here we are introduced to a new planet that has 1/3 of the gravity of the Earth. And then for jumps with the same force on both planets, which of the following is true? And we're given a bunch of fractions here. So we're looking at J, so the equations that we're going to look at are these equations here. And these equations, we're already told, are true when the force is the same. And so that's helpful because we're looking for the same force anyways. So these formulas have been derived from this, and also the fact that gravity on the moon is 1/6 that of the gravity on the Earth. And so given the fact that gravity on the moon is 1/6 of that on the Earth, we can see that to get J moon, we have to multiply K Earth by 6. And so if we extrapolate this to our new planet, we're told that our new planet has 1/3 of the gravity of the Earth. And so if we're following the pattern here, then our equation should be this. Okay, and so just using pattern recognition here, just for speed and so that you're not using too much prerequisite knowledge as well. So C is constant. So what we can do is when we're comparing these fractions, we're going to have to cancel it out anyway. So for simplicity, let's just get rid of C. And then let's look at the different proportionality. So looking at A, we have J moon, and let's plug it in. So J moon is 6K, and I'm just going to leave it at K because we're looking at Earth in all three, so we know we're looking at K Earth, so I'm just going to say K minus 1 over 3K minus 1. And it's saying that this is greater than 6K minus 1, which is the moon, over K minus 1. Now, what you can do here, instead of trying to figure out exactly what these values are going to be, we want to just look at what's greater on the numerator versus the denominator, right? So over here, we have 6 over 3, and over here we have 6 over 1, right? So we have quite a large number here and a medium number here, right? We just want to compare a large number here and a tiny number here. So the larger your numerator is, the larger your value is going to be. And the smaller your denominator is, the larger your value is going to be. So here we have a large numerator which is going to increase our value, and we have a small denominator, which is also going to increase our value. So this side is going to be greater than this side, right? So comparing those numerators and denominators allows you to do this calculation without actually having to figure out the exact values. So this is going to be incorrect, right? And if you think about it logically, the jump that you experience on the moon, let's look at this one, moon, versus the jump you experience on the earth, if you're looking at the gravity is 1/6 here. So you're going to jump approximately 6 times as high as you are on the earth. And then over here, it's a similar situation. You have 1/6 and 1/3. So if you're comparing these two, the gravity on the moon is half of that of the gravity on this planet, right? So you're going to probably jump around 2 times as high. And so this 2 times as high is not nearly as big as 6 times as high. So this inequality is incorrect. In fact, the opposite would be true. And here we have in our option B, the opposite. So we have jumping around 2 times as high here and jumping around 6 times as high here. And so, like we looked at here, this value would be greater than this value, not looking at any specific numbers. Now, options C and D are tricky because they actually give you these values here. And so these are hard and fast values, right? That you have to sort of calculate. So if we're looking at J moon and J planet, we have J moon being 6k minus 1 over 3k minus 1 is equal to 1/3 times 6k minus 1 over k minus 1. All right. So what we're given here is a bit of a calculation, and you can't really simplify these bits any further, right? It's just going to have to be, you would have to know the value of k for each of these in order to solve this, right? And so you can't confidently say that this here is always going to equal this here. Okay? Because with the same force, your k could be different. All right? And so although with these ones, you can get kind of the approximate, oh, it's going to be greater than this or less than this. Here we're being asked to say equals. Equals to 1/3 times this value here. So let's try to plug in different values of k just to check this. So I've just cleared the board here to make it easier to follow along. What we're going to do is just plug in a random value of k to see if this holds true. So let's say k is equal to 2. Okay, so we would get 12 minus 1 over 6 minus 1 is equal to 1/3 of 12 minus 1 over 2 minus 1, right? So we would have 11 over 5 is equal to 1/3 times 11 over 1. And so this bit we can multiply that and we get 11 over 3. So obviously 11 over 5 is not equal to 11 over 3. So that disproves C. And then we would go through and just check the last one as well. 6k minus 1, so that's J moon, over 3k minus 1 is equal to 2. So let's plug in k equals 2 again. So we have 11, like we got earlier. So 12 minus 1 is 11. And then over here, we have 3 times k, which is 6 minus 1 is equal to 5. So 11 over 5 does not equal to 2. So that disproves D as well. all right? And the thing is, what you could have done here, you could have done that same thing for these as well. So if you have J moon over J planet, so let's plug in the values of 2 again. So J moon over J planet, we've already established, is 11 over 5. And then you have J moon over J earth, which over here, if we were just doing this little bit here, is equal to 11 over 1. Right, so we've just plugged in a random k value here. We can see that because number 5, well, we can see from this that 11 over 5 is less than 11, right? And so that would have disproved this one, and you would have been able to circle B. So that's another strategy that you could have used. This question required pattern recognition and just being able to work with fractions without kind of getting bogged down into the details of specific values, and being able to work with proportions that way. And also subbing in random values. That's another reasoning technique that you can use if you're unsure. You can just sub in values and see if those things work, especially if you have 4 options like that, if you're going to be using the process of elimination. And so the bootcamp resources that can help with this are the acceleration class on calculations and formulae, as well as the reasoning skills course, and then just, again, the bridging course on work and forces to be familiar with that pre-knowledge as well. And that brings us to the end of this unit. So please like, share, and subscribe for more GAMSAT help. We really value your feedback. We have our Instagram at Thank Flip GAMSAT and our podcast, Thank Flip GAMSAT, Nurses Doing GAMSAT, if you want to hear more from us. All right, I'll see you in the next one.